All right, have you ever looked at a giant high-res map on your screen or an image with a huge, perfect blue sky and wondered, how does a computer store all that without just running out of memory? Well, today we're diving into the incredibly clever data structure that makes it all possible.
I mean, think about it for a second. Storing every single blue pixel in that sky seems so wasteful, doesn't it? It feels like there should be a smarter way. The challenge isn't just to store the data. It's to capture the essence of the grid without getting bogged down in every tiny detail. We need a way to just say, hey, this whole massive area is blue, and be done with it.
And the solution to this exact problem is a really elegant structure called a quad tree. It's tailor-made for handling two-dimensional data like this, and its name pretty much gives the whole game away.
At its heart, a quad tree is all about one simple action: division. The name says it all, right? Quad means 4. So the whole idea is to take a square area, and if it's not all the same, you just chop it into 4 smaller equal squares. And you keep doing that, drilling down into the details, until all you're left with are simple blocks that are all one value.
Now, to make this whole system work, the tree uses 2 different kinds of nodes. And as you can see here, everything comes down to that is-leaf property. If a node is a leaf, that's the end of the line for that part of the tree. It means, hey, this block is all one value, our work here is done. But if it's not a leaf, we call it an internal node. And its only job is to be a parent, to say, nope, it's mixed in here, and point to 4 new child nodes that will dig one level deeper.
So, how do we actually build one of these things? We use a legendary strategy from computer science called divide and conquer. And honestly, the name tells you everything. We're going to take our big, complex grid and just keep breaking it down into tiny, simple problems until each one is an absolute piece of cake to solve.
And this right here, this is the entire playbook. It's beautifully simple. Step 1, you look at a grid square and ask one question. Is this all one value? If the answer is yes, you follow step 2, you create a leaf node, and you are done with that branch. Simple. If the answer is no, you go to step 3. You create an internal node, and you divide that square into 4. And then, this is the magic right here, step 4 tells you to just repeat this entire process for each of those 4 new, smaller squares. That repetition, that's recursion.
Okay, that might still feel a little bit abstract, so let's make it real. We're going to walk through a very simple 2x2 grid to see exactly how this algorithm plays out in the wild.
So here's our grid, a little 2x2 with a mix of zeros and ones. You can see right away it's definitely not uniform, so we know our algorithm is going to have some dividing to do.
Okay, starting from the top with the whole grid, we ask our most important question: is it uniform? Well, with both zeros and ones kicking around in there, the answer is a very clear no. And since the grid isn't uniform, our rules kick in. We have to create our very first node, an internal node, to represent this whole mixed-up region. And then we do what the algorithm does best: we divide. That 2x2 grid gets split into 4 little 1x1 quadrants. And now the recursion really begins. We run our logic on each of those 4 new quadrants. The top left one is just a single cell with a 0. Is it uniform? Of course. So it becomes a leaf node. The top right is a single 1, also uniform, so it becomes a leaf node too. And you can see the same logic applies to the bottom left and the bottom right. This is what's so cool. Dividing the problem simplifies it all the way down to these super easy base cases. And just like that, we're actually done. The final structure is one single root node, that internal node we started with, acting as the parent to 4 children, all of which are nice, simple leaf nodes. We've just efficiently represented our mixed grid.
Okay, so that's the logic. But how does this nice, clean idea actually translate into code? Well, you might be surprised to see just how closely the code follows the simple rules we've just been talking about.
Just take a look at this side-by-side comparison. Our plain English rule, check if the grid is all the same, well, that's just a simple if statement in code. If it's true, we create a leaf node. If not, we go to the else block and create an internal node. And the really beautiful part? That final step, repeat the process for each subgrid, that's just the function calling itself over and over again. The code is a direct translation of our logic.
So the key takeaway here really is this. Don't get intimidated by the code. The heart of the solution is just one recursive function that perfectly copies that checker divide logic we've already mastered. Seriously, once you understand the rule, you basically already understand the code. Okay, this has been a fantastic puzzle, but why does it matter outside of, a computer science class? Well, quad trees aren't just some academic exercise. They represent a fundamental concept with some really powerful real-world applications.
So why is this so important to know? Well, first, efficiency. For that image with the giant blue sky, a quad tree can represent that whole area with just a single leaf node. That's a huge space saver. Second, it's a perfect intuitive example of the divide and conquer strategy, which is just a cornerstone of programming. You see this pattern everywhere, in image compression, in geographic map systems, you name it. And finally, if you're prepping for technical interviews, this is a classic. It's a fantastic way to prove you really understand how recursion works.
And that brings us to the final, really powerful idea. We've seen how divide and conquer works for a 2D grid, but this approach is so much bigger than that. It's used for sorting lists, searching through tons of data, even rendering complex 3D scenes. The principle is always the same. Take a big, intimidating problem and just keep breaking it down into smaller, manageable pieces. So the question I want to leave you with is this: what other complex problems in your world could be simplified by applying